Welcome to this demonstration of hypothesis testing for the difference of two population proportions. The context for this example is the Hamilton ACO. Specifically, we are interested in the outcome of smoking, and we're going to restrict attention in this particular example to adults within the Hamilton ACO beneficiary population. The leadership team is concerned about the proportion of beneficiaries who smoke and whether or not that differs between those Medicare beneficiaries who are dually eligible for both Medicaid and Medicare versus those that are not. So to expedite the problem, I've gone ahead and written down some background information here on the number of smokers within the dual and non-dual populations relative to the total number of adults in each of those two groups. We also can write down explicitly our null and alternative hypotheses. We're interested in investigating whether there's a difference in the proportion of smokers between the dual and the non-dual populations at Hamilton ACO. The status quo, or null hypothesis in this case, is that there is no difference, that we wouldn't expect there to be a difference. The alternative, of course, is that there is a difference, and this is a two-sided test. Also, before we get started, let's make our statement about our significance level. Here we're going to use alpha equal to 0.05, corresponding to making a type 1 error probability. We want that to remain fairly low. That is, we want to be convinced that there's enough evidence to reject the null hypothesis in favor of the alternative. So here we have a two-population hypothesis test of proportions. And to get started, we need to, of course, to remember that the test statistic for this type of situation or context follows a normal distribution. So I'm going to write out the test statistic here to remind you of that. So specifically, we have three parts. We have the point estimate of the difference, which is going to be p bar dual minus p bar not dual. I'm going to subscript that with an ND, minus the value under the null hypothesis, which is just 0 in this case, divided by the standard error of the difference of two proportions, which is going to be equal to the square root of PC times 1 minus PC times 1 over n non-dual plus 1 over n dual. Okay, close parentheses here. So we have some of the pieces already, but we need to do some calculations before we can plug into the equation. So let's come back here for a second and extract the information from our summary table to arrive at our key pieces of information. So the first is our p-bar dual, which is the sample proportion of duals who smoke, and that's just equal to 134 divided by 481. Which equals 0.279. And the sample proportion of non-duals who smoke, that's just equal to 406 divided by 2675. That's equal to 0.152. Now, the third piece of this, which is a little bit of a twist relative to other things we've done, is this P sub C, or combined or pooled proportion that we need to construct. Specifically, we can construct it by essentially adding up these two divided by these two. And so it's just the combined proportion here, which sometimes is denoted with a bar across the top since it's a sample as well. And just for the sake of expediency here, when we do that, we get 406 plus 134 divided by 481 plus 2675, and we get 0.171. Okay, we're combining both of those samples together. All right, so the next piece of this, and for some variety here, I'll switch colors. We're going to now move to incorporating that information into our formula to calculate our test statistic. So let's do this now. So we've ordered the hypothesis as the proportion of dual minus the proportion of non-dual. We want to maintain that ordering as we go through the test statistic calculation. So let's substitute in our information. We start with 0.279 minus 0.152 minus 0 divided by 0.171 times 1 minus 0.171 times 1 over 481 plus 1 over 2675. Okay, so we've got some calculations here, and when we go through that calculation, assuming my math is right, which we always hope, is we get a test statistic of 6.79. So as before, we of course need to now evaluate that test statistic relative to our critical value or values given the standard normal distribution. So I'm going to go ahead and draw that distribution down here. You've seen this before. The standard normal distribution is a symmetric distribution, which makes life a little bit easier here. And the standard normal does not have any degrees of freedom to worry about. It is a single distribution. So we had said that our significance level was 0.05, and here we're doing a two-sided hypothesis test. That means in practice that we're going to have two rejection regions, one in the upper tail and one in the lower tail, each having 0.025 in probability underneath them, with 0.95 in the middle. We're next going to arrive at what is the value on the z distribution corresponding to this particular probability level. And what we know is that given that the standard normal doesn't have any degrees of freedom, we can either look on a standard normal table or use Excel to arrive at our values. In this case, we are going to have values of 1.96 and minus 1.96. I just know this from teaching statistics for 20 years, so, but you should feel free, of course, to look it up as you need to. All right, so now our last piece is to compare our test statistic of 6.79 relative to our critical value of 1.96. So our test statistic is really kind of out here, way out in the tails. Okay, so our test statistic is more extreme than our critical value, and that allows us to conclude or to have evidence to reject the null hypothesis in favor of the alternative. That is, our sample evidence is sufficient to convince us that the proportion of smokers in the dual population is different from the proportion of smokers in the non-dual population. Now, as an alternative to a two-sided hypothesis test, we might have been interested in doing a one-sided test. And in particular, perhaps we're concerned that the proportion of smokers in the dual population is greater than the non-dual population. That might warrant some additional intervention. The key difference in our methodology, if we were going to do that, would be in two places. The first would be how we express our null and alternative hypotheses. In particular, we would write this down as p dual minus p non-dual less than or equal to 0 versus p dual minus p non-dual greater than 0. The other place that this is applicable is around our determination of the critical values. In particular, if we were to do an upper one-sided test, all of the rejection region would sit in the upper tail, and we would still compare our test statistic to that particular critical value. In this instance, if we had maintained our assumption about alpha equal to 0.05, our critical value would be 2.33. In that case, we also have evidence to reject the null hypothesis in favor of the alternative because that test statistic of 6.79 is larger than 2.33. We would then conclude that the proportion of smokers among the dual population is higher than that of the non-dual population. This concludes our example of hypothesis testing for the difference of two population proportions.